Imagine you're building a pristine 175 billion parameter AI engine.
Right, a massive undertaking.
Exactly. You've got the architecture totally dialed in. The data pipelines are flowing. Everything looks just perfect.
Yeah, on paper, it's flawless.
But then to actually make that machine learn, you realize you have to strap on an additional like 350 billion invisible parasitic parameters just to get the gears to turn.
Oh, it's brutal.
Suddenly your hardware is just screaming, your memory is completely maxed out, and you are staring at this massive physical limit. So welcome to this deep dive.
Thanks for having me.
Tonight we're settling into a bit of a relaxed late-night radio groove. We are looking at some incredible notes from the LLM Mastery series.
Yeah, it's a great series.
It really is. And our mission today is to focus on the engine that makes AI learn, the optimizers. We're talking Atom, AdaFactor, and the wild stuff beyond that.
It's the hidden overhead that just makes traditional software engineers want to pull their hair out.
Totally. Because for a software engineer transitioning into AI, understand the code is, well, it's really only half the battle.
Right.
Understanding how the model actually updates and learns, that's where the real magic happens.
I mean, you think you're optimizing the model, but really you're fighting the optimizer itself most of the time.
Yeah. But before we get to the cutting edge of AI training and all these hardware limits, we have to start at the absolute foundation.
We do. We have to go back to the baseline.
Right, the foundation, how models learn. And the notes start with stochastic gradient descent, or SGD.
Yeah, pure SGD.
And I love the exact phrasing from the source here. They call it beautifully simple.
And from a mathematical standpoint, it really is beautifully simple. I mean, it comes down to this core philosophy.
Okay.
Imagine you're trying to find the absolute lowest point in a vast, dark, uneven valley.
Like you're blindfolded.
Exactly. You can't see the whole landscape at all. You can only feel the ground directly beneath your feet.
Yeah.
So what do? You feel the slope. You take a step in the direction that goes downward.
Makes sense.
Then you stop, feel the slope again, and take another step. You just keep doing that. You calculate the error, which is the slope, and you adjust your parameters just a tiny bit.
Okay, let's unpack this. If pure SGD is so beautifully simple, why did we even need something new?
Well, because the valleys we're exploring in deep learning are not smooth bowls.
Right, they're not simple.
No, they are unimaginably complex, high-dimensional spaces. What if your valley has a really long, flat ravine or thousands of jagged little false bottoms? Pure SGD has zero memory.
Oh, wait, so it doesn't remember where it just was?
Not at all. It only knows the exact slope under its feet right at that exact millisecond. So it ends up just bouncing blindly back and forth across a ravine.
That sounds incredibly inefficient. In software terms, that's like hard coding a basic loop with a single rigid timeout for every single API call.
Yeah, that's a perfect analogy.
Whether it's a massive database query or a tiny ping, it just blindly reacts with the same rigid step.
Exactly. And that rigid inefficiency became a massive bottleneck. So we needed something smarter.
Right. Which brings us to the game changer mentioned in our text, the Atom optimizer.
Yes, Adam.
Published in 2015 by Kingma and Ba. So how did Atom fix this bouncing problem?
Well, it combines two specific things. First is momentum.
Momentum. So moving away from the blindfolded guy taking single steps.
Right. Imagine replacing that person with a heavy boulder rolling down the hill.
Okay, a boulder. I like that.
A boulder gathers speed, sure, but more importantly, it carries directional history.
Right. It had physical momentum.
Exactly. If it hits a tiny, jagged ravine, the momentum just carries it right over. It doesn't violently change direction just because the slope shifted for a fraction of an inch.
It acts like a dynamic system that remembers past momentum. That makes total sense. But the notes also mentioned it combines momentum with adaptive per parameter learning rates.
Right, and this is why it completely dominated deep learning.
So what does that mean in practice? Adaptive per parameter.
In pure SGD, every single parameter takes the exact same size step.
The one-size-fits-all thing.
Yes, but Atom dynamically adjusts the step size for every single variable independently.
Oh, wow. So for every single parameter.
Every single one.
That's like having a dynamic load balancer that tracks the historical latency of every individual endpoint in your whole system.
Exactly. If a parameter is jumping around too much, Atom shrinks its step size. If it's stuck, Atom increases it.
That's brilliant. No wonder the text says it completely dominated the field since 2015.
It did. But as models grew exponentially, the very features that made Atom so brilliant suddenly became a massive physical constraint.
Right. The memory wall. But before we hit the wall, we need to talk about how practitioners actually used Adam.
Yeah, the L2 regularization.
Right. Because left to its own devices, a model will find shortcuts. It gets greedy.
Oh, they totally cheat. They'll blow up a handful of weights to massive numbers just to force the math to match the training data.
So how do you stop that? The text mentions combining Adam with L2 regularization.
Yes, L2 regularization. The source explains this means adding a term to the loss function that specifically penalizes large parameter values.
Got it. So it's like a mathematical rubber band keeping the model in check.
Exactly. The bigger the parameter gets, the harder the rubber band pulls it back towards zero. It keeps the model mathematically stable.
Here's where it gets really interesting, though. We have Adam, we have the L2 rubber band. Everything is mathematically sound.
Yep.
But then we look at the sheer scale of modern AI. The notes point to a model with 175 billion parameters.
This is where it all breaks down.
Right.
Yeah.
Because in traditional software engineering, a slightly bloated variable isn't a huge deal. You have tons of RAM.
Not here.
What happens to Adam's math when we scale up to 175 billion?
Well, this is the critical constraint from the source text. Adam requires 2 state variables per parameter.
Wait, 2 state variables per parameter.
Yes. One to track the momentum, the boulder, and one to track the gradient history for the adaptive learning rate.
So for 175 billion parameters,
You're tracking 350 billion extra variables.
that's a serious engineering problem. I mean, the source explicitly calls it that.
It is an absolute crisis for hardware.
You're loading 175 billion parameters plus the 175 billion gradients plus 350 billion atom states.
Right. The intelligence of the model is entirely dwarfed by the memory footprint of the system just trying to update it.
It's this wild clash between algorithmic elegance and just strict hardware memory limits.
It really is. And human engineering hacks like compression techniques, they only delay the inevitable.
Which perfectly sets up the final section of our notes. Because if human-designed optimizers like Adam hit this insurmountable memory wall at scale,
You have to change the game entirely.
right, the only way forward is to change who or what is doing the designing.
Yes.
So here's the big question raised directly by the source. Instead of humans designing optimizers based on mathematical intuition, what if we let a machine search for the optimal optimizer?
What's fascinating here is the profound philosophical and practical shift this represents.
How so?
Well, we're stepping away from human mathematical intuition. For decades, it was humans imagining rolling boulders and rubber bands.
Right, human metaphors.
But now, we're effectively outsourcing the core design of AI learning back to the machines themselves.
Using techniques like symbolic regression, the note said.
Exactly. Setting up massive evolutionary search algorithms. You give the system basic math operations and let it breed thousands of algorithms.
Testing them, keeping the efficient ones, mutating them.
Generation by generation, yes.
As a software engineer, that is just wild to think about.
It is.
It's the equivalent of writing a program whose sole job is to invent a better compiler than a human ever could.
And they succeed. They find bizarre algebraic combinations that humans just don't have the intuition to conceptualize.
Wow. So, just to bring it all together for you listening, we've journeyed all the way from the beautiful simplicity of pure SGDs.
Taking tiny steps in the dark.
Right, to the 2015 dominance of Kingma and Ba's Adam, combining momentum and adaptive learning rates.
And then we hit that massive memory wall.
Yeah, the 175 billion parameters crashing into Adam's 2 state variables per parameter, plus L2 regularization keeping it all in check.
A literal physical limit.
And finally, we looked at this futuristic concept of machine-designed optimizers, outsourcing the math to the AI itself.
It's a completely new frontier.
It really is.
Yeah.
And it leaves you with a pretty lingering question, honestly. Something to mull over.
What's that?
Well, if we successfully let machines search for and design these optimal optimizers, what happens when they invent a mathematical approach that works perfectly, but is so alien that human engineers can no longer understand the underlying intuition?
That's a scary thought.
Are we really comfortable with the very engine of AI becoming a total, impenetrable black box?
I guess we'll find out.
We will. Keep exploring the deep end, everyone. We'll see you next time.